In this lesson, we'll explore how Pascal's law makes it possible to lift a massive weight using a surprisingly small force. So, Pascal's law says that a change in the pressure applied to an incompressible enclosed fluid is transmitted to every portion of the fluid and to the walls of its container. So, it'll be transmitted here, 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 and whatever point you can think of within this container. So let us use this setup that has a liquid and these two pistons with areas A1 and A2. Okay, before we proceed, it's important to note that we can ignore atmospheric pressure in this analysis because it acts equally on both pistons, cancelling out any net effect. Now, we apply force F1 on this piston that would create an added pressure delta P equal to F1 upon A1. Now, Pascal's law states that in a sealed, incompressible resting fluid, this delta P should appear throughout the fluid and therefore on the big piston as well. So, let us see what happens here. Since delta P appears here as well, we can say that the upward force generated here due to delta P would be F2 is equal to delta P into A2. And if we put this delta P, we get F2 is equal to F1 upon A1 into A2. And let us rearrange this a little and write in this way, that is F2 is equal to A2 upon A1 into F1. Now, since A2 is much larger than A1, this factor becomes large and therefore F2 becomes much larger than F1. So you see, with some effort here, you have force multiplication this side and this piston would go up. And this magnified force can be put to several uses, one of which is lifting large objects like say a car. So if this body weighs W Newton and force F2 is more than W Newton, we will be able to raise this mass. Now, we can develop a deeper understanding of this topic if you also try to understand when will this body come to a stop, as in it cannot keep rising due to this force. So, at static equilibrium, that is when everything ceases to move, the added pressure from the small piston must balance a load on the large piston plus any hydrostatic head from their height difference. So, if we consider this level, here the upward pressure should equal the downward pressure, or F1 upon A1 should equal W upon A2 plus rho G delta H. And if they are at the same height, that is the delta H term is 0, we find F1 upon A1 equals W upon A2. That is, the upward pressure is balancing off with the weight of the body. Another important point to note is that by no means is Pascal's law saying that energy is also getting multiplied like force. So, let us show that no energy is getting generated in the process. Now, we know that the fluid is incompressible. So, volumes that move down here must rise here, or A1 D1 should equal A2 D2. That means D2 is equal to A1 upon A2 into D1. So, the big piston moves a much smaller distance and ideally work in equals work out. That is, work done on left hand side is F1 D1 and on the right hand side is F2 D2, and the two should be equal. So if you substitute this for D2 and this for F2, you get work done on the right hand side, which equals A2 upon A1 into F1 into A1 upon A2 into D1. That you see turns out to be F1 D1, or the same work done as on the left hand side. Simply put, big force into small distance is equal to small force into big distance. there is no free energy.